Welcome to the SolidCAM UK Technology Centre. We're planning to show you a series of webinars to replace our regular lunch and learn events. So, what's different? We're still having partners, we're still having SolidCAM engineers making demonstrations, and we're cutting metal live and interactive. So there's no real difference apart from you don't get any lunch. So throughout the demonstrations and throughout the event, we'll be having a live chat feed. That means you can type in your questions, ask the engineers any relevant questions about what's going on during the day, and we'll try and answer those interactively. If we don't get through them all during the event, we'll get back to you afterwards with a quick call and chat about the whole thing. So enjoy the day, ask questions, and we look forward to seeing you all again when we're allowed to do that. Thanks and enjoy your day.
Thank you, Gordon, and welcome everybody to SolidCAM Live. As you can see, we're currently live in our Barnsley workshop. Hi, I'm Ian, and on my left is Ben, our applications manager.
Morning, everybody.
This morning, between us, we're going to be taking you through our presentation, which should last maybe an hour or so. During the presentation, we'll be getting live contributions from our industry partners, who are Romi Machines, Fenn Tools, Heimer Tool Holding, CG Tech Vericut, Shunk Wheel Holding, and Bloom Probing. Okay, I'm going to pass you over to Ben. Let's get started, and he'll give you an introduction to the workshop.
Yeah, thanks, Ian. So, as Ian mentioned, we're in Barnsley Technology Centre. As you can see, we've got two machines on my left here. We've got the Romi D1000. We've also got the 5-axis machine that came in just this week, so that's brand new to us at the moment. We've also got a lathe as well, a GL series in the corner that's just out of shot from what you can see there. We're going to be running live cutting on the D1000 today, and we're just going to have a quick presentation of SolidCAM. I'm going to show you a bit of iMachining, show you what we're doing on this machine today, and then when we come back we'll be able to see it cut in the part that we've shown you. So we'll have a look at that presentation now.
So we're first going to have a look at a presentation of SolidCAM. We're going to have a look at the features and benefits of SolidCAM, and we're also going to have a demonstration inside the software as well of the part that's been programmed for today's seminar, how it's been programmed, and then we will cut back to the cameras in the machine to have a look at this being cut live. So SolidCAM are leaders in integrated CAM. The major benefits of using SolidCAM inside SolidWorks are that we have the same look and feel through a seamless single window integration. There is full associativity inside SolidWorks as well, so any model changes that are made will automatically update the toolpaths in SolidCAM. SolidCAM is working inside the SolidWorks assembly mode to define fixtures, tooling and vices, and we've also been gold partners with SolidWorks for the last 17 years. We have a complete integrated solution inside SolidWorks. We are a modular system, so we can add the specific modules needed and when needed as well, so you don't have to have all the modules all at once. If you buy a new machine and need extra modules, these can be plugged in afterwards. Moving on to our iMachining module. So this is our high-speed roughing operation inside SolidCAM with a technology wizard built in as well. So we get increased productivity due to shorter cycle times, up to 70% and more cycle time saving. We dramatically increase the tool life and unmatched hard material machining as well. We see outstanding performance when using small tools, and we can use iMachining on 4-axis machines, 5-axis machines, mill turn machines as well. High programming productivity and a very short learning curve. The unique wizard will optimize the feeds and speeds for you, including the depth of cut based on the stock and the tool material, as well as the machine specifications. So this takes the headache out of programming these high-speed roughing operations. So iMachining comes in 2 stages, all built into the same operation. The first stage of iMachining is to create an intelligent toolpath, so an efficient tangential toolpath which will ensure constant tool load on the machine. And then the second part of iMachining is the technology wizard. This will calculate the cutting conditions for any given machining operation. So this will calculate things like the speed, the feed, the depth of cut, and also the cutting angles. So we can have variable cutting angles. You can see there from 80 degrees to 10 degrees we can have set the maximum and minimum cutting angles based on what we wish to achieve, or we can let the wizard handle those maximum and minimum based on the material parameters that it's been given. You can see there on the left hand side at 20 degree engagement the feed rate is a lot higher than it is on the right hand side at 50 degree engagement. So iMachining will fluctuate the feed rate based on its engagement and its contact points as well. Also, the patented unique features inside iMachining are we have the morphing spirals only in iMachining, as you can see there on the left, so with a varying width of cut. And on the right hand side we have intelligent separation as well for iMachining, so we can separate areas with channels to maximize the spiral area. You can see there on the left hand side we're machining up to a wall. Now once we're machining up against the wall we're going to be full engagement with the cutter. So what iMachining does is it separates this section out and machines in a sort of lace strategy here against the wall, and creates these 2 channels here to leave 3 final areas for spiraling. So you can see on this next slide here we now have the 3 morphing spiral areas that are being machined by iMachining. This is more efficient and better for the tool. So optimal speeds and feeds for iMachining. So the technology wizard will calculate these speeds and feeds for you based on data that we have initially entered. So we would initial the material properties. We obviously select the geometry that we want to machine. We have the tool geometries and we put in the machine parameters. This will then calculate all of these that we see in red here. So the technology wizard will calculate the depth, the feed rate, the step over and the spindle speed, all synchronized together. Now the depth of cut is calculated inside iMachining, and it is calculated on an optimal depth of cut to reduce vibration. We're looking for an ACP close to a whole number. Now if you look on the left hand side here, ACP1, that is 1 full engagement with the tool. This is minimal vibration. If we look on the right hand side here, we have many contact points and we have an ACP of 4.5 as we hit the top, so we have a gap. Now this will produce vibration based on the fact that the tool has load and there is a flex point at the top here. With this one here we're in full contact on the left hand side here. Now the cutting forces are only now in one direction, to the left. On here an ACP of 3 would be fine as well, so we're looking for an ACP closest to a whole number as we can. And again iMachining will calculate this for us. iMachining is a patented technology. No other system can use our technology. You may see other systems using the spiral or morphing toolpaths, but you won't see any system using a spiral toolpath and also calculating the speeds and feeds and depths of cut using our technology. So let's have a look at a demonstration of the component that we're actually cutting live on the machine today. So this is the component that we're cutting today live in our seminar. As you can see, we have two operations on this component. So first of all, operation 1, we start with a blank billet of material, and we are holding this in the shunt vise in the double pot system, and we're holding it up, and we are then going to use some iMachining to initially rough out all of this material here, and then we're doing some general machining and finishing on the inner shapes, and then chamfering around the top on operation 1. Now, operation 2 is where we then turn the component over. We already have this shape machined, and we're now holding it again using the shunt double pot system, but now holding it in the diaphragm that has the shape cut into it. So this will hold the component down while we machine the second operation. So if you have a look at the iMachining on the second operation here, you can see where I'm machining out the center and all the way around this outside shape. Now these outside walls are actually tapered, so as you can see here, iMachining is actually doing a full cut, and then it comes back up the wall to produce a cusp on there ready for finishing, and that is done in the technology section. I have applied rest roughing and told it to create a maximum scallop of 0.5 after it's finished its initial roughing of all the meat. Now just moving on to the wizard, the technology wizard here, this is where we are looking for the ACP. Now we're at 1.97, you can see it's nice and green in there, so we have a nice green chart telling us that this is optimal cutting conditions. We are close to a whole number there, so we will get those optimal cutting conditions. If I go to the tool, you can see we're using one of Fenn's bullnose tools here. So this is a 12mm tool with a 0.15 rad on the corner. It is a 4-fluted end mill, and it has a 37-degree helix on the flutes. If I was to change the flutes, for instance, let's say this only had 3 flutes. If we go back to our iMachining, you'll see the technology wizard has changed. The speeds and feeds here and the step over have changed, and now we're into the orange section. We're at 1.48 ACP. This means that we're likely to get vibration from this component now. The tool is not suited to cutting under those conditions. So I'm going to go back and I'm going to alter my flutes back to it being a 4-fluted end mill. That was just to show you there that the technology widget is actually using the data that we've input to calculate its operations and calculate its speeds and feeds. Let's have a look at another operation here, these 2 operations here. Now these are finishing the walls and finishing the floors. Now this is a 3-axis machine we're running on, the Romi D1000. So we can't tilt, we're not using 5-axis in this particular instance. So what we've actually got is a taper tool from Fenn. So if we have a look at this tool here, you can see we actually have a taper tool, corner radius on there of 1.5, taper angle of 4 degrees. Now the tool can actually cut on the bottom as well. So what we've done here is this first operation is we have machined around the walls, and then the second operation we've machined the floors, and we've got the rad on the tool as well that is the same as the radius on the bottom of this component. So as we go around and machine that taper and then machine the floor, we will blend the radius into it, leaving no witness marks because we're using the same tool for both operations. So I'm just going to show you a simulation of the iMachining in Solid Verify. So this is iMachining simulation here. You can see the tool starts from the outside and we get the nice morphing toolpath as we move in between those blades. We've got a constant engagement there, and we are varying the feed rate. You can see the feed rate is constantly changing. If I expand this a little bit more, you'll see that the cutting angle is also varying. So the cutting angle and contact points are changing at the same rate. They are synchronized with the feed rate. So the lower the cutting angle, the faster the feed rate, and the greater the cutting angle, the slower the feed rate is. If we just move on and show you the taper tool working in simulation as well. So this is what the iMachining has left behind, and if we just slow this down, you'll see the taper tool come in. It takes a couple of roughing cuts at it, so we're stepping inwards towards that face there. It has no problems cutting on the floor. It's designed to cut with the bottom of that tool. So as we go around and we generate that radius, or leave the radius behind with the radius that's on the tool itself. So one last finishing pass there as we go around, and then we will cut the floors with that same tool. So again, having a nice blend on the floor in a nice concentric pattern, creating a good finish on the floor, as well as maintaining that blend and leaving no cusps behind. So let's have a look at this cutting live on the machine tool.
So that was the presentation there on iMachining. The material we're cutting, you can see there the machine's running. The material we're cutting is EN24T. We've got a few questions coming in here as well. I've got a question of my own first. Did you order the bacon sandwiches for everybody this morning, Ian?
Oh, I forgot, sorry.
Yeah, you had one job, Ian, one job. Yeah, so some of the questions coming in. 70% time saving, what is this compared to? So it's compared to traditional roughing strategies where you would be doing a small step down with a larger step over, maybe. Still probably running at quite high feed rates, but we're using the full flute length of the tool. So compared to traditional roughing strategies, the time savings are one element of iMachining, but also the using all of the carbide, using everything that you've paid for, less pressure on the machine, less pressure on the spindles. There's all sorts of different benefits on there as well. So I hope that answers that question there.
Okay, there's another question here. Does the material type have effect on the benefits that you can gain with iMachining?
No, we can use iMachining with any material type. So we can use it on softer materials like aluminium. We're using a mid-grade or quite hard steel, really, N24T. We can use it on titanium as well. You still get the same time savings and benefits that you would from any other material. you'd see more benefits from a harder material. So we're boasting upwards of 70% cycle time savings. When we sort of get into titaniums, you're looking into the 80s and 90% cycle time range there of the savings. So.
There was another question, but I think you've kind of covered that. The question was the benefits of using an end mill rather than a toroidal button cutter in iMachining.
Yeah, so that goes back to the traditional roughing strategies, really. So instead of the smaller depth of cut, we're using a large depth of cut, small step over, and a really high feed rate. You can see that this one here, we're running up to a feed rate of 7,000 millimeters a minute. So that's quite a feed rate at 19.2 millimeter depth of cut. We're going to have you can see this is running obviously on the Romi D1000. Just have while that's running now, just have a quick presentation from Eduardo at Romi Machine Tools. He's going to tell you all about their company and what other machine tools they supply as well.
Hi everyone. First, I'd like to congratulate SolidCAM for this event. Our company is happy to be part of it, among other very good companies that are also participating here today. So thanks for the invitation. Well, talking about Romi, we are a 90 years old company that for decades we have been manufacturing and selling machine tools, injection molding machines, and machine casting around the world. We are proud to be one of the few OEM in the world to take care of the entire manufacturing process of the products we sell, including the casting, the machining, the wiring, the sheet metal, assembling, etc. Which means that we have everything in our hands, not having to rely on some Asian suppliers, for example, so we can guarantee a lifetime support for our customers. I used to say that one of the main attributes of our machine tools, our CNC lathes, VMCs, HMCs, VTLs, and so on, is the robustness. Considering we have our own foundry as another business, we know about casting and both engineering, our foundry and our machine tools engineering, they have all the synergy to make the optimal machine structure. For our customers, it represents high rates of swarf removal and a stable and reliable machine, which means shorter cycle time, less scrap, and in the end, more competitiveness. Well, today, as we can see at SolidCAM, we have three machines. So the first one is the Romi GL240M. This is a turning century with CX and driven tools. It has 175 millimeter chuck with tool setter, part catcher, bar feeder preparation. And this machine usually we sell for medium and high production for parts up to 260 mil diameter by 400 millimeters long. But still you'll see it's a very compact footprint. The second machine is the D1000. This is a 3X VMC with 10K spindle, 30 tools capacity, high pressure coolant pump through the spindle. This machine offers all the flexibility of the VMCs, but with all the robustness of Romi machine. It still has a Siemens 820D CNC, which comes with the conversational programming shop mill, making the setup and more programming simpler and faster. The third machine, the last one we see here today, is a 5-axis with 15K spindle. This is really a full 5-axis machine, and it's a good fit for simple parts with more than one side to be machined, but also for very complex parts that require these 5 simultaneous axis interpolation. Well, if you have any question about one of these three machines or any other machine from our portfolio, please do not hesitate to contact our team here in our headquarters in Rugby. I hope you all enjoy the seminar today and the live demos. Thank you again, and everybody stay safe. Bye.
Yeah, thanks for that, Eduardo. As you can see, they've got a full range of machine tools that they can offer, and they obviously give us a lot of support as well in our technology centre with these machines. One of the questions come in here as well, just back to iMachining. Can you use an indexable porcupine tool with a large diameter? yes, it would come under the same, because you've got a sidewall on the cutter to use. It would come under the same category as using an end mill. So yes, you can use that with iMachining. There is another question on the taper tool as well. Is it a special? The taper tool has been supplied by Fenn tool. I don't believe it's a special. It's off the shelf, a 4-degree taper. We're going to talk about that a little bit more when we get to the using the taper tool, because that's going to be on the second op of this part. So.
Just on the point of tooling, we've had a question about, is it only carbide tooling where you can make savings in iMachining?
No, it's not just carbide tooling we can use with iMachining to make the savings. We can use HSS and cobalt. We've also got the option in there for carbide and premium carbide as well. So all that does is just increases or decreases the feed rates and the adaptability of iMachining. So you still make time savings. We're still using the full depth of cut, whether using HSS or carbide.
Right. There's another question here about where the majority of savings are made when you're using iMachining. Can you tell everybody sort of where those savings come from?
So yeah, the savings come from us doing a small step over with a large depth of cut. That's the cycle time savings, but we've also got savings on the carbide. We're using all of the carbide. We're not notching it at a certain depth. We're using the full flute length. We've got savings in respect to the machine tool itself, so less pressure on the bearings and the spindle. There should be a lot of savings all round. There are a lot of benefits to iMachining. As you can see, we've just switched tools now, so now we're using a high feed cutter. So this is a 10mm bull nose with a 1.6mm rad on there. That's roughing out that 3D shape in the centre. We're running at 6,300 millimetres a minute with a 0.5mm depth of cut on this tool as well. Now the holders that we're using here on this in this seminar have actually been supplied by Hymer. You can see they're all heat shrink holders. And we're just going to pass over to Phil Crawley from Hymer, just do a quick presentation on what they're about and their company. He's going to show you around their showroom they've got there as well. So let's just have a look at that now while we finish this roughing off here.
Good morning, everybody. I just wanted to take you on a virtual tour of the Hymer UK headquarters here in Burnley, just to show you what facilities we have here and what may be of interest for you to come and visit. So we start with our entry-level Uno Smart Presetter, just ready to sit next to the machine tool, giving fairly basic measurement but still a very accurate piece of equipment. This is supported in our tool management wall here, which is leading round to our balancing unit, our tool dynamic for high precision balancing of tool holders and any assemblies you may have, and following around some displays. So on balancing technology, our torque wrench, cutting tools, duo lock, cool flash and safe lock. A lot of people don't know we also are able to provide grinding wheel arbors with a facility to balance. Now the balancing unit, which is our tabletop version, more of an entry-level machine, and to our shrinking, which is the product that we're mainly known for. Following on with the displays of different tool holder types, and coming around to our more advanced presetters. So our Uno Premium here with a 700 column with a completely manual machine, and then onto our Violineer, which is a fully automatic CNC controlled machine with all axis driven. And of course we have a conference area with a TV for presentations. If anybody would like to come and see our facility, please just give us a call and make an appointment. Thank you.
Thanks for that, Phil. It's a nice facility they've got there. If anybody does want to obviously get in contact with any of our partners, if you've got their contact details, you can obviously contact them directly. If not, just feel free to give us an email or give us a shout, and we'll pass those details on. You can see the machines now using that same cutter, that 10mm bullnose cutter. We're now finishing that inner 3D shape. So this is using HSS, which is another one of our operations inside SolidCAM. We're using high-speed surface strategy. So on this particular part, we're using blend between two curves. So we're blending between the outside shape and then a circular pocket shape in the centre. So that gives us a nice flowing toolpath. Gives us a nice constant step over as we go down there as well. Have we got any other questions in, Ian?
Yeah, have I got a question here about, is it best to use coolant or to cut dry when you're using iMachining?
So when using iMachining, we're generally cutting dry. We're trying to keep the heat in the material and the cutter. So we're working on a heat curve. What we're trying to do is heat up until we get to the top of the curve, and then continue to ramp up until the heat curve starts to drop off the back. So we're actually getting the material to cool itself by going faster and hitting it harder. So using coolant is not recommended with iMachining. Maybe when we go for softer materials like aluminium, we may want to put some coolant on there, but make sure you've got a good constant flood supply on the tool to maintain the heat, rather than heating it, cooling it. Otherwise you will sort of thermal shock the tool and the material. Just another question regarding iMachining. When using a cutter with a variable pitch, what helix angle would you input into SolidCAM? So you generally go for the mean, so go for the middle. If you've got a helix pitch of 35 to 38, generally go for sort of 36.5, 37 helix. That will give you a good enough calculation for iMachining to continue, really. We changed the cutter over now, so now we're using an 8mm tool, an 8mm M-mill, just round the outside, just finishing round the outside profile. On there, we've got a bit of chamfering left to do on this here as well. After that, and then that will be op 1 complete. We'll change the part over, and we'll start showing you op 2. Anything else from your side?
I'm just going to say, once we've completed this, obviously we're going to show how the chuck system works. I believe you've got a presentation from Marcel at Shunk coming up.
Yeah, we've got a presentation shortly when this is finished.
Okay.
And we'll obviously Shunk will be able to tell us about the equipment they've supplied us here for the work holding. So at the moment we've got it gripped in a vise. You can't really see it on the camera there, but we'll show it a bit more detail shortly. But the vise is in the double pot system that they've got, the pneumatic system that pulls down the vise. So 0 point setting to put the vise in the same position every time it goes in. What we'll do for op 2 is we're going to take this vise off, and we're going to use a diaphragm system on that same double pot system. We're going to use a diaphragm to actually pull the part down. So just while that's just going to finish chamfering, and then that's that side complete. So just while that finishes the chamfering off, let's have a little presentation from Marcel at Shunk. He's going to tell you all about the system, and then I'll show you changing it over live when we come back as well.
On behalf of Shunk, I would like to thank SolidCAM for inviting us to this webinar. Shunk offers a complete range of solutions, from the lifting of the part to the final assembly, going through chucks, tool holders, vices and automation. Today we will be talking about the work holding solution inside the machine. For this demonstration, SolidCAM are using a VeroS, our 0-point system, in combination with an SPM fixture, a membrane-like solution. The SPM always requires a VeroS to operate, so we'll briefly go to the main points. For those not familiar with 0-point, it comprises of one or multiple plates fixed to the machine bed and a pin attached directly to the part or to a vise or to any other work holding equipment. Our 0-point solution is pneumatically activated, so all you need is a 6-bar air feed to operate it. Virtually all CNC machines have an air feed, making the system a plug-and-play application. The locking is done using springs. That means there's no need to keep the system energized during machining, so there's no need for air through the table. The operator can plug an air pipe, drop the part, pull the pipe, and setup is finished. The locking capacity is incredibly generous. If it fits inside your machine, it will hold it. Repeatability is 3 microns. Set it and forget it. Once you set the system in place, there's no need of readjusting the setup. It's fail-proof. The fact that the system can run without being energized also means that if you have a power cut or any other machine interruption, the work holding is not going anywhere. Shunk system is unique regarding the sliding tolerances. That means that you can have a wide angle or off-center parts and the locking will happen anyway. Particularly important when you cannot see or if you're handling very large items that will swing on the crane. So moving on to the SPM, the flexible diaphragm system. It's a highly customizable fixture. Think of this as a DIY custom fixture with amazing value for money. Here you can see the part on the top, which can be of any profile machinable, the SPM itself, and the VRS base on the bottom. So what is it capable of? The depth of grip can go from 3 to 20 millimeters, holding force is 50 kilonewton, and the work diameter goes from 36 to 125 millimeters. The stroke is 0.5 millimeter, and that's what you use to set up the clamping force. The bigger the gap you leave between a machine profile and the actual part profile, the lower the force. The tighter the gap, the stronger the force. It's self-centering. It can be remachined to suit other parts, much like any soft jaw. Setting up, all you need is a VRS pin going through the bottom. You machine the profile as required, and it goes on top of the VRS, covering completely, preventing from any swerve ingress. So it's important to highlight that you don't need one of these per item. You can combine different profiles within the same item. So what we try to demonstrate here is that you could use one SPM for 2 different ops, for example. So you would hold your parts on the larger diameter, the blue circle, and that would cut your first op, which is that orderly shape profile. Then you can flip the part over, lock on that orderly shape profile, and go through your op 2. So let's have a quick video to see how that works. So here you can see the 2 air pipes in and out, 50 kilonewton of clamping force. So air goes in, 0 point unlocks. You can see the SPM has already been cut to shape. There's a pin attached to the bottom and a centering pin on the edge. It goes in. Once you pull the air off, it locks and pulls the membrane down. That's your locking action. So now it has been released. Part goes in, air comes out, and is locked. Simple as that. And now we can see a very aggressive cutting strategy here, and the fixture remains rock solid. So in summary, it's a very flexible application which can be at the same time gentle to a machine surface and extremely strong holding the part with any variety of profiles. So this is it for us. If you have any questions, please forward them to SolidCAM and we will follow them up. Enjoy the rest of your webinar.
Thank you, Sal. Interesting stuff. What we're going to do now, Ben's going to take the part out of the machine and give you a quick look at the camera. Just show it to the... there you go. So that's the part after op 1. What he's going to do now is going to change the holding system. So what he's going to do is take off the vise, which is currently held in the 2-pot system as we described earlier. So as he attaches a pneumatic device, it releases the clamps, so that enables Ben then to be able to take the vise off. The pneumatics control the springs, so what Ben's going to do now is replace this with a diaphragm system. So it just covers up one of the pots because we're not using it, and there you can see the diaphragm with the shape cut in it. So that shape is the same as the end of op 1, so it's the finished size. This is pre-cut second operation. So Ben's now going to put that into the pot when he's cleaned it up. So once this goes in, Ben will release the pneumatics, and once he's released it, this will then clamp down on the system. There you go, it's just cleaning it up. So Ben's introduced the part into it, so as he takes it off, you may just be able to see the diaphragm close down. and what he's doing is applying it to the second hose fitting, and that exerts a force behind the springs as well. So now we're ready to start op 2. So Ben's taking off his working clothes, because obviously he's just been working for a living for a few moments then, and we're ready to go on op 2. So I'll hand over to Ben.
Yeah, thanks Ian. So as you saw, yeah, it's the quick change system, just 0 point setting as well. So the diaphragm is basically like a collet. Once you put the air and load the air behind the springs, it will pull the collet down and squash into the part. We've obviously forced, like you saw in Marcel's presentation there. He explained that as it sort of pulls it down. And now we're into iMachining again. So this is 3D iMachining this time. There's no difference in the application of 2D iMachining to 3D iMachining. 3D iMachining just, in terms of the software, just means that you can just tell it to cut a whole part rather than a prismatic shape. So we're cutting a 3D shape here because the walls are going to have tapers. So we're cutting the full depth of cut first of all, and then it will go around and it will then recut at a 0.5 step down, just to generate the cusps up the wall ready for finishing. So you can see there it's got a full cut on now as it's going around the component.
We've got a question.
Yeah.
Is that part in full lockdown, Ben?
Yeah, that part's now in full lockdown. We did have to isolate it for a couple of weeks, but now it's in full lockdown like the rest of us.
And the other question is, do all the parts have to have that star shape in them in the diaphragm to fit the diaphragm?
So no, the components don't all have to be the same shape. That star shape's been pre-cut into the diaphragm by ourselves. What you do is you cut it with a setting ring underneath the diaphragm first of all, and then when you take the setting ring out and you put the part in, obviously the diaphragm pulls down even further, which squashes in further as well. So you can cut different shapes into them. As Marcel showed in the video there, you could have a shape there for op 1 and a shape for op 2, obviously cut at 2 different depths so that you can maintain the gripping for both operations. You could, if you were just doing one-offs as well, you could start with your smallest component or smallest shape and then just keep opening it out to different shapes as you sort of begin to use that diaphragm as well.
The 2-stage clamping system that we use then, I kind of glanced over it a little bit. Can you just explain a little bit more about how that works in practice?
Yeah, so the 2 stages, you saw the 2 ports on the front. You can still see them there on the camera. 2 ports on the front. So one port on the left there releases the spring so that you can take the diaphragm off, or you can take the vise off there. Now, when you take the air off that, the spring's force will push back in and pull the diaphragm down a little bit. The second port is then for loading air behind those springs. So you put the air on, it pushes those springs and the pins inwards, and then when you take it off, it leaves the air behind it loaded up. So there's no need to have air in the table. It's fully locked down now. There's no way that can be released without putting air back on it. So like Marcel said, if you've got a power cut, if you've got failings with any pneumatics or anything, that won't affect the clamping of that part at all. Now, I mentioned earlier we're using Fenn tooling or Fenn tools for this presentation and this seminar. So this cutter here is a 12mm end mill. It's running at a maximum feed rate of 4,600, depth of cut of nearly 25mm, cutting all of that material out there. Let's have a quick presentation from Fenn Tooling about what they can do and what they can offer. You'll see there the taper tool that they've supplied us as well in their presentation. So I'll just pass over now to Mike Dixon from Fenn Tooling, who's going to walk you through some of their products.
Hi there, and welcome to the SolidCAM seminar with Fenn Tool. Fenn Tool Limited was founded in 1982 by Peter Fenn. We're located in Braintree in Essex, and also have a sister company, Kildare Tooling Services, which was founded in 1993 by Peter. This is located in Kill in County Kildare. One of the tools used in this demonstration, the 32408R10, is an 8mm 5-fluted cutter with 1mm radius. This has a variable flute and helix and makes it an excellent tool for toroidal milling. With an aluminium chrome nitride coating, it makes it a good all-round tool for machining steels all the way through to super alloys. The range goes from 6 to 20mm and has a 0.5 radius through to a 5mm radius. This will be dependent on the size of the tool. The 3251200 is our 12mm variable indexed helix tool. This is used for ramping to do the internal part of the bore and then opening out to the sides. It has a raised profile and it has an aluminium chrome nitride coating. This makes it a really versatile tool for covering a full range of materials. When we first started discussing this project, we wanted to show the versatility of the software, but also the versatility of Fenn being able to produce something slightly different tooling wise. So we decided on a special tapered cutter. So the tool was designed by our R&D department, a drawing produced. The drawing would normally be sent on to the customer then to sign, just to say he's okay with the dimensions, and then the tool would be made. It would then go to our manufacturing facility, and we are one of the leading UK manufacturers of solid carbide milling cutters. The UK manufacturing facility is based in Braintree in Essex, and that was opened in the year 2000. We are ISO 9001 certified. We have an intensive R&D program which is used to develop new tooling. Modifications to standard tools to meet specific requirements from customers. This can be going from necking to radiuses or any slight modifications on tools. This can be done. And we have a competitive turnaround from quotation to delivery. And here we have the finished tool. At Fenn, we have a company mission, and that is to deliver our services and products to the highest of standards and strive for consistency in everything we do. Our brand promise is our product quality, customer service and company performance deliver the results that differentiate us from our competitors. I'd like to thank you for sparing your time today. I hope you found the demonstration useful, and if there's anything that came from this demonstration that you need any more information on, then please don't hesitate to contact us. Thank you.
Thanks Mike for that presentation. As I said before, we've worked quite closely with Fenn Tooling on this seminar as well. I mean, not too close, we're still social distancing. So we have got another question in there. What spindle speed, feed rate, step over and depth of cut are you using? So on this particular bit of iMachining, 3D iMachining here, we've got a 12mm end mill. The step over is just less than 1mm, so just short of 10% step over. The spindle speed is 4,800 and the feed rate is 4,600 millimeters a minute. The depth of cut is 24.6 millimeters, so nearly 25mm depth of cut. We're using that full flute length on there. A question here as well, what tool radius would you recommend as a maximum for iMachining? As I'm aware you don't support ball nose cutters. So we would not recommend ball nose cutters obviously for roughing in any instance, especially not for iMachining. You want a minimum radius on there. It's really just to stop the corner of the cutter chipping whenever you do any roughing strategy, really. On this particular tool, there is a 0.15 chamfer on the end of the end mill. And on the first tool that you saw, the 8mm on the 2D iMachining, that was a 1mm rad on that tool as well. So you can have a radius on the bottom, but I wouldn't go to the extremes of nearly a ball nose cutter. So I'm just going to hand over to Ian now. Maybe he's going to tell us a little bit more about some of the other products in SolidCAM. Maybe he can talk about HSM.
Yeah, absolutely. Thanks, Ben. HSM is another product available from SolidCAM, containing multiple strategies. It's predominantly aimed at the mould and die industry, and whilst it can be used for other work, it's particularly well suited to this type of work. HSM works particularly well direct from the model of the die or the form. It doesn't matter how many surfaces there are. Basically, you tell it what the model is and tell it what your cutter is, and it will work out the strategies based on which option you've picked. All the time it's doing this, it's fully protected against all the surfaces and the work holding and any fixturing you might have. HSM has numerous strategies, about 20 in all, most of them aimed at finishing. So we've got vertical finishing, horizontal finishing. We've got combination, so we can work between vertical and horizontal, where the system will identify the cutter contact angle and will automatically change from steep to shallow. This means we don't have to create any manual boundaries. We can then go into radial, spiral, morph machining, offset machining, 3D constant step over, pencil milling, and then rest machining to finish the part off. So it's a very, very powerful strategy. Ben, I don't know if you want to tell us some more of the advanced features in SolidCAM?
Yeah, so we've got obviously more advanced strategies in SolidCAM as well. So there's we go up to 5 Axis Simultaneous. We've got mirror machining and translation options as well. You're going to see that in a presentation I'm going to show you shortly. We're going to do some mirror machining, some 5 Axis Simultaneous, some barrel cutting. We've also got support for Swiss type and advanced mill turn machines as well. So another question here, can iMachining be used in 3+2 and 5 axis? Yes, of course it can. It can be used, it's a 3-axis toolpath, but you can index to a face and use iMachining. There's no simultaneous 5-axis iMachining. We're purely 3-axis roughing operation here as well. Another question there, what's the cut time and what is the standard cutting time compared to the, so basically what are the savings on this particular component? So when I run this on a normal sort of roughing strategy in simulation, we're looking at sort of 60% cycle time saving on this particular bit of iMachining here, this 3D iMachining. The cycle time saving is quite considerable compared to what we would do in a traditional roughing strategy. Now we've also got Bloom as a partner today as well. We're going to see some probing. We've got Bloom probing on this component here. We're going to use it in combination with a Rigibore automatic boring bar. So the boring bar is going to come in. We're then going to probe the bore, and the boring bar is going to adjust itself. And then we're going to probe the bore again, and then the boring bar is going to adjust, ready for a final finish cut, and cut that as well. So just while this iMachining finishes off, it's just roughing out that bore in the middle there that we're going to actually bore out. We'll have a little presentation from Paul Hodgkinson at Bloom Nova Test.
Hello everybody, my name is Paul Hodgkinson from Bloom Nova Test UK. I hope you're enjoying the SolidCAM event today. I wanted to give you a quick whistle-stop tour of Bloom, and if you'd like to know more, my contact details are on the very last slide of this presentation. Bloom was started over 50 years ago by Gunter Bloom and is still family owned to this day. We now have over 600 employees worldwide and a UK subsidiary set up in the year 2000. We have a dedicated team of engineers in the UK who are experts in retrofitting probes to CNC machine tools and will fully support the installation with training and are able to be fully contactable once the installation has been completed. The ethos of Bloom is to ensure that every single part that the CNC produces is a good part. We achieve this by measuring both the cutting tool and the workpiece inside the machine tool. This ensures minimal downtime and maximum productivity of the machine tool. You will be able to see our touch probes in action today, but I wanted to let you know about our new LC50 Digilog laser system. This is the next generation of laser measuring technology and uses a digital system to measure tool breakage and also an analog scanning capability which provides thousands of data parameters on the state of the cutting tool. Our high-quality touch probes are a very cost-effective way of ensuring that the measurement process of the workpiece and the cutting tool is automated into the machine program. This ensures that every single part that is being produced is good every time, increasing productivity. And you can see by some of the features and applications that we have here, we're all about ensuring that every single machine is working at maximum productivity and increasing automation and ensuring minimal operator involvement. Thanks very much for your time today, and I look forward to hearing from you soon with any questions or queries you may have. I look forward to hearing from you soon. Bye-bye.
Thanks for that, Paul. So as you can see, this is the taper tool running around the outside profile of that component now. We've not got coolant on just for the cameras, so you can see we've got a bit of heat in the tool there. You wouldn't normally expect that once we've got coolant on there. So this taper tool's running around the outside. It's doing a bit of a roughing cut first of all. It's going to keep stepping in, and it's also going to cut the floor of that component as well. So the first cut there was quite a large cut. That's why we saw all the heat in there. I'm just going to pass over to Ian as well. Anything else you'd like to sort of add?
Yeah, we've actually got a question. Does SolidCAM have the ability to program for the probing? I know you mentioned the Bloom earlier.
Yeah, so we can fully program the probes inside SolidCAM from any manufacturer. Obviously, we're working with Bloom. They're one of our partners. But we can do either part datum setting, and we can do full inspection as well. So we can do measurement on the machine. So we could do in-process inspection as well as datum setting with the probing.
Thank you. This might be a good time to maybe talk about some of the other things that SolidCAM can offer. Yep. As well as being a software provider, we like to think of ourselves as a solution provider. As you can see, we've got this great facility here. We've got lots of technology and lots of equipment to be able to use. So we're more than happy to utilise that for customers and prospects and working with partners as well. So we've got the ability to call on industry partners to help us look through a particular project that a customer might be looking into. It may just be that they just need to do some strategic planning on a part, and again, we're quite happy to sort of bring the part in here and try and go through it with the partners and find out the best way of doing it. The partners we use are all specialists in their own fields. This helps us go step by step through any client's particular needs and find a solution. This offers the client not just the confidence that our software is capable of doing the job, but sort of in conjunction with our work holding, tooling, verification partners, it gives us the ability to show that we've got a seamless integration between our system and their products. So that kind of makes it easier for customers or clients to be able to look and say, actually, that's going to be the right solution for me. Part of this, and one of the other things we offer, is the ability to write the post processes. So this is something that Ben and his team deal with. So Ben, would you like to tell us just a little bit more about what you and your team do with post processes?
Yeah, so all the post processes and all services are done from the UK. Full support inside the UK. We write them ourselves. We're not getting them from an external source. So any things that need changing on a post process or any support that's needed is all done from here in the technology centre itself, actually. So we have a team of engineers, including myself, who all do the training from here. We can do remote training. We can do training on site as well, obviously when lockdown permits us to do so. We can also do application days. We do support from here as well. We've got the ability to do remote support. We can do screen sharing and things like that. And we also write all the post processes. We just now got a sort of separate section as well for specific Swiss type post processor development as well. So we've got engineers dedicated just to doing Swiss type post processors. So we get them absolutely spot on for the customers. like we need them to be. Any more questions sort of coming in from there?
Just having a quick look. I can't.
So that's the taper tool just finished there. I put a stop in the program because now it moves on to the boring bar and the probe. So I'm just going to switch to the machine camera. I'm just going to show you this step by step, and we'll talk through it as we go along. So the rough boring bar is going to come in first. So the roughing boring bar is just a preset boring bar. It's got automation on it or anything like that. It's just going to come in and take a skim out of there and leave 0.3 inside that bore, ready for a semi-finished cut. Now once that rough boring's happened there, you can see it's gone away now. It's going to go for the probe. So we're going to pick up the probe when it's come round in the carousel. These boring bars are big boring bars, so they've got dedicated pots. So the probe's going to come in now. It's going to probe the bore, and what I'll see, you'll not be able to see it on camera, but what we'll see on screen is it will tell me the size that it's probed. Once it's size, I don't need to do anything with that information. I've put a stop in again just so again I can talk through it. So it says here the bore size is 49.8, so it's left 0.2 on inside that bore. Now that's fed that information back now to the automatic boring bar. So you're going to see a different boring bar come in now. So this is the automatic boring bar, and it's going to have adjusted itself and set itself to within 0.05 of the bore, ready to do a semi-finished cut. Now again, it's just changed to an empty pot because the boring bar is so large. We've got a dedicated pot. So you can see here the big white bit there is the sensor for this boring bar. So you can see it's taken a rough cut. We've moved out, and we're going to go pick the probe up again, and we're going to probe this bore and see what size it comes out at this time. So that was the semi-finished cut. It should be within 0.05 of the finished size. The size we're aiming for is 50mm. It's going to be the finished size of this bore. So probing again using the 4-point probe strategy. So I got a message on screen again. Now the bore is 49.92. So we're within 0.08 of the finished size. So I'm going to set this off again. That information has now been fed back to that boring bar. The boring bar is going to adjust itself by the amount it needs now to cut the bore to 50mm. So we'll see this boring bar come in again. So quite small adjustments it's making again automatically using a little system it's got. This is all a closed loop system, so it's all being fed back automatically from the probing system inside the machine tool. So like I said, this boring bar has been supplied by Rigibor through Fenn Tool. So Fenn Tool are one of their agents. So the probe's coming in again now, and now we should have a finished size come up on screen. So the size it's telling me now is that bore is 50.012. So within 0.012 of the finished size. So that was the boring bar and the probing in action there. We've got another tool coming now. We've got the finishing the flat areas. So we've got an 8mm bull nose in here with a 1mm rad on the bottom. It's just finishing inside the floor of that bore now. We've told it to stand off the walls by 0.1 as well, so we're not going to touch the walls. We've got a nice fine finish on that bore. So after we've finished the flat areas, we're going to come to a bit of chamfering, and then we're going to put some logos on the part, and that will be this part complete. So Op 2 will be complete, and we'll finish this part off. So I've got a question in here as well. Is the auto boring bar system operated by Bloom or Rigibor? It's operated by Rigibor. It's the Rigibor system inside. So Bloom probing simply stores the size of the bore inside a variable on the machine. The boring bar then picks up that variable, picks up the number from that variable, and uses that information to do its own maths and calculations on how much it needs to adjust. What diameter is the part, so I can get an idea of size? The diameter of this part is, I think, is 110 millimeters. The center bore there is 50 millimeters. So that's an idea of the size of this part that we're cutting today. Any more questions your side coming in, Ian?
There's nothing come across this side, but obviously using the tooling from Fenn and the collaboration that they've got with Rigibore, I mean, I think maybe one point you have to make out is that the parameters need to be set in your machine by Rigibore themselves, don't they? So somebody needs to come and set that parameter for you.
Yeah, so Rigibore would come and set up the boring bar initially, but obviously you could then just continue to purchase their boring bars and use them. You don't have to have every boring bar set up. Once the machine's set up ready to accept these boring bars and use them, then you're good to go, really. Bloom probing is just standard bloom probing. It's all it's doing is feeding that variable, that number back into the variable that the Rigibore boring bar can then use. As you see, we've got the chamfer cutter in there now, so we're just chamfering around all those little blades on there. The chamfer does get quite close at this point.
Isn't this the operation where you put a toilet roll in the fridge?
It's the operation where you put a toilet roll in the fridge.
You got a bit close.
Yeah. So we're chamfering all the way around the side. The next tool coming in is going to be the engraving tool to do the logos. That's going to be a 1.5mm ball nose cutter. It's quite a small cutter on there. We're just going to engrave the logos 0.1 deep into that component. We're going to have a logo right in the dead center of that bore, and then we're going to have a logo on each one of those little flat areas in between the blades as well.
Yeah, that's getting pretty close, isn't it?
Yeah, the holder gets pretty close, but we've got full collision detection inside SolidCAM as well. So we've got the machine simulation. But what we've also got as well is we've got a good partnership with Vericut. So all these toolpaths that you see today, they've been verified through Vericut as well, after we've post-processed them out and verified them in SolidCAM. So Vericut work quite closely with us. They supply us the machines for these as well. We've just obviously taken the 5-axis machine into the shop this week as well, and Vericut have already supplied us with the machine configuration for Vericut for that as well. So we'll be using that on our next seminar to verify the code before we start roughing out or before we start machining, on that machine. So, while we're talking about Vericut, these logos finished. You can't really see the logos being done at the moment, but once the part's finished, we'll actually, I'll take it out. I'll show you on the camera. We'll see the logos on there as well. Couple of questions coming in first of all, just before we move on to Vericut. The cutting noise seems very quiet. Does iMachining reduce the noise levels? iMachining does reduce noise levels as well. That's been proven. It's been proven in shops that were using traditional roughing methods. They've had a decibel meter in there and measured the noise levels, and then they've switched to using iMachining and had all their machines running iMachining, and there's sort of significant drop in the decibels being produced by the cutting as well. So yeah, from a health and safety point of view, everybody needs iMachining. So yeah, we'll pass over to Vericut. Let's have a little presentation from Tim Mitchell at Vericut. He's going to tell us all about what they do and all the different machines that they support as well, and machine types.
Hi, my name's Tim Mitchell from CG Tech. This is going to be a short video showing you the features and benefits of Vericut software. Vericut is the world-leading software package for verification, optimization and simulation. Vericut simulates real-time NC data and uses a digital twin to prevent costly crashes on your actual machine. Due to the modular design of Vericut, customers can choose the capabilities that they need specific to their requirements. The verification module reads in the same post-processed G-code and will highlight any issues prior to the NC code getting sent to the machine. Machine simulation enables full realistic 3D simulations using the true digital twin with the most accurate results from any other package. By using the multi-axis module, customers can check any simultaneous axes, whether it be milling, drilling, turning, or any other functionality that they need to simulate. Additive. This enables our customers to use Vericut to simulate and check the processes when using hybrid technology. Force optimization can significantly reduce machining times and improve the process by protecting the spindle and your cutting tools. Charts can assist in the cutting process by identifying areas of concern or areas for improvement. This can be used on new or old programs to ensure efficient and safe running throughout. Composite applications. Vericut can assist with the programming, verification and simulation of the automatic fibre placement processes. VCP is the programming package available and VCS is the simulation package available. Vericut can run independently or with the use of an interface from SolidCAM directly into Vericut. Save time, save money, save your machines.
Yeah, thanks for that, Tim. So a real insight there into what Vericut can offer and all the different machine types that they can support. So we're going to have a quick presentation now on a few of the other areas of SolidCAM, including 5-axis and some Swiss type stuff as well. So 5-axis capabilities and barrel milling inside SolidCAM. So with powerful simultaneous 5-axis toolpaths with a friendly user interface. This user interface is the same as the rest of the SolidCAM interface. Collision checking and avoidance for tool, holder and other machine components like the fixturing and the table and things. Specific application solutions as well for swarf, multi-blade, port, contour. We've got multi-axis drilling, conversion of HSM to simultaneous 5-axis. There's also screw machining as well. So these are all dedicated to those specific areas, making it quite easy to produce programs and toolpath for these types of parts. And we've got simulation of the whole machine tool as well in machine simulation, showing the motion of all the rotary and linear axes. We've got 3 and 5-axis mirror machining capabilities as well, so we can reverse the toolpath to maintain the cutting direction. That's done automatically when we mirror a toolpath. Obviously the ease and speed of programming for handed parts, so being able to program a left-handed part and then just easily mirror the whole program across to a right-handed part makes it quite easy. We can mirror using the same datum, so we can keep the datum the same and have the same or one datum for two components. We can mirror about a new datum, so we can have a separate datum for each individual component, and we can add operations to the end, so you can complete one part and then machine complete the second part, or we can optimize it inside the operations as well, so we can, whilst we've got one tool out, we can do everything on both components with that tool, then move on to the next tool. Some of the barrel milling supportive tools in SolidCAM, we see there we've got barrel shape, oval form, taper form, and the lens shape as well. So we can do 3 and 5 axis toolpaths with barrel cutters inside SolidCAM. So tool manufacturers promise a 90% or up to a 90% reduction in machining time when using barrel milling tools. And you can see the benefits here, and you can see where those that reduction comes from. Circle end mills offer a larger step over while maintaining the same cusp height, so require a smaller step over with a ball nose end mill to produce that same surface finish or same cusp height. You can see there on the left hand side we've got a ball nose cutter 0.5 contact point there, and on the right hand side we've got a barrel mill with a 1.5, and the surface finish is actually better. So if you wanted the same surface finish as you've got there on the left, you could even increase that to 2mm, 2.5mm, step down and create the same surface finish. Some other benefits to barrel milling as well. Obviously we've got the low cusp height, but we've got balanced machine inaccuracies as well, smooth transition between the cuts, and low dynamic disturbance due to shorter tools. So because we don't have to, we can tip over to use the barrel tool. It can be a lot shorter than a standard end mill. You can see there on the left hand side there, if we're running an end mill down a wall, you can see that the forces acting on the side of the tool there to push it over would generally create a small cusp on there. Now with the barrel cutter, if the force, the same force is applied there to the side of the tool and it kicks over, you'll generate the same cusp as you were if the tool was actually vertically upright, because of the shape of the barrel mill itself. You can see here Y circle end mills as well, some more reasons. So tools with barrel section can be tilted, so we can reach in further. You can see that there. We've got collision on when the tool is vertically upright, either an end mill or a barrel mill, but as soon as we tip the barrel mill over and we're still using that same radius, we can get down a lot further. And also some circle end mills can be used on their flank for wall machining, so we may have a radius on the bottom of the tool and we can actually come up the wall, or we can create small radiuses in the bottom using the same tool, so we can minimize any blend issues that we may have. You can see here as well, we can either have the tool static, so we can pick a point on the barrel mill where we can scan down the wall, keeping a single point contact along the whole contour, or we can be more dynamic and we can have the contact point change from the contour start to the end, so we can give it a starting contact point, and we can give it an end contact point, and as it moves down the wall it will adjust its contact point to maintain that step over and cusp. And in terms of 3-axis barrel milling, you can see there on the left hand side we've got a lens tool which is of barrel form. That's a 10 diameter tool with a 20mm radius on the bottom, and a 2mm corner rad. So actually this was running at a 1mm step over. We did run this at the last seminar. This was one of the benefits we showed of barrel milling against a 10mm ball nose to create the same surface finish. We had to run that at 0.1mm step over. So you can see there that that's 90% cycle time saving just by adjusting the step over. So that's with the same speeds and feeds and everything consistent, just by changing step over from 0.1 to 1mm and using the same diameter tool. we've actually achieved 90% cycle time saving. And in terms of 5-axis, we can see here again the comparison. On the left hand side here we have a 6 diameter barrel with a 95mm rad and a 1mm corner radius on the bottom. Now this is running at 3mm step over to create the same surface finish as a 12mm ball nose would be at a 0.2mm step over. You can see also as well on the ball nose we've had to tip that ball nose over quite a long way to achieve the contact, whereas the barrel mill is nearly upright, which means we've got less chance of collision as the table banks over. So we'll have a little look at this in the software, then a little demonstration in the software, and then we'll have a look at some other features inside SolidCAM. So we can see here, this is the part being demonstrated. We've got some barrel milling on here inside this little deep pocket. This is that 6 diameter tool that you saw with the 95mm rad. You can see it's kicked over to the same angle as that side wall face there as we go down the face, and then we start to pick out the radius at the bottom. We can see this in solid verification here. You can see it machining those sidewalls, and then we pick out the radius at the bottom, and we also scan up the radius in the corner, and then we come over and machine that wall separately. Now this section here is showing mirror machining, so you can see there I've highlighted all of the operations in there. I'm going to select to mirror about a plane that's been created in the middle of those two parts. We're creating a new operations in position, and we're doing this on a new Mac position as well, so a new datum. You can see that it's easily mirrored all of that toolpath, and if we see that in full machine simulation, it's mirrored the 3-axis toolpath as well as mirroring the 5-axis toolpath with that barrel cutter. You can see it machining one component, then the other component, and then changing tools and coming back and machining the next component. So that was 5-axis. We're going to have a look at advanced mill turn and Swiss type inside SolidCAM now as well. So we can see here we support all turning operations and composite turning tools. We do simultaneous 4-axis turning as well, updated stock for both turning and milling. And the toolpath calculations also take into account the tool and insert and tool holder. We've got things like balanced roughing, angled grooving, manual turning, 4-axis simultaneous turning, multi-turret synchronization. We offer easy programming for complex mill turns and Swiss type CNC machines with multi-turret and multi-spindle. You can see there the image on the right hand side there. We've got twin spindle, twin turret. The upper turret is a B-axis. The subspindle also has a tilting or a rotary axis on it, and we can support all this different configuration. We offer MCOs, so we can insert control operations while manufacturing a part, so we can insert custom features and functions, and mill turn parts also support iMachining 2D and 3D, so we can still do iMachining in a mill turn type environment. So regarding the Swiss type support that we've got unlimited, we've got support for unlimited number of axes and channels inside a mill turn post processor. So you can see there on the left hand side that is an example of a Citizen Swiss type machine, and 7 axes, and on the right hand side there we've got a Star SR38 machine which has 10 axes on there. The channels can be split into either turret or by spindle, and again we can have any number of channels. We've got full support there for our channel synchronization, so you've got full control over that, and we can even import and export different channel synchronization setups. So a few examples of different Swiss style machines that we support inside SolidCAM. Again, this is not all of them, we support any number of configurations. You can see a few more there as well, and some of the programming that's been done inside SolidCAM on these machines. So let's have a look at again a little demonstration inside the software of how this works. So this is a component we've got here being machined on a Citizen style post processor. If we go to the channel synchronization here, this is the window. You can see on this machine we've got 3 channels. So we also support the different axis patterns as well that this machine may have, so we can switch the different axis patterns on the synchronization markers. If we have a look at the machine simulation, you can see we can simulate all the axes moving. You can see we've got the main spindle and the back spindle both simultaneously working and synchronized here on the left and right hand side. We can see it live there. So this was cut as an example. We've got the turning on there. We come back to machine simulation. We can see full simultaneous milling on our component as well there. So you can see we've got a B-axis on this machine with a bank of tools, and again, so we can fully support indexial positioning with that B-axis, or we can support simultaneous work. You can see it in action there live on the machine. We have that simultaneous surface machining being done on that component.
Thanks very much for that, Ben. Great presentation on what can be quite complicated machines. For those of you who think it's Groundhog Day seeing Tim twice, slight technical glitch, so just prove that we're live. Anyway, we're going to carry on. What Ben's going to do now is he's going to take the part out of the machine, and he will hold it up to the camera for us, so you can get a bit of a look at the engraving that he's done. And there you can see the logo in the middle. Very nice part, well done. So we're going to kind of wrap things now. We're just going to have a quick chat about this new machine that we've got, the 5-axis. So Ben, if you'd just like to sort of talk through this new.
Yeah, so as you can see, we've got the 5-axis machining like we spoke about earlier. This came in on Monday, so it's pretty new to us, but we're going to do our next seminar on this machine. It's a full 5-axis simultaneous. The next seminar is going to be the 16th of July. We'll be sending out a link very shortly for everybody that's attended this seminar, and obviously we'll be marketing it as well. So if you know of anybody that'd be interested in watching another one of these seminars, obviously completely different next time, different machine, different part. So yeah, I hope you've all enjoyed this seminar today. I hope everybody's got something out of it. If we haven't answered your question, we will get back to you shortly. There was another question actually on there as well, just as I had a look there. Mirror machining, does it reverse the toolpath, i.e. climb and conventional? Yes, it does. It's intelligent enough to know that when we mirror the toolpath, the direction should change as well. It becomes a completely new operation, so climb milling is still respected. So as I say, I hope you've enjoyed the seminar. I'll pass back to you, Ian, just to close it off.
Okay, thank you very much, Ben. Thank you very much for attending. This is our first foray into live presentation, so I hope that there hasn't been too many glitches and everybody's been able to see it okay. I personally would like to thank Ben for all his efforts, because he's put all this together. I'm just studying, I'm the monkey, and he's definitely the organ grinder. So very much appreciate his efforts. We hope to see you again next time. Like Ben said, if you've got any questions, please forward them on to us, and we'll answer everything we can. So for today, thank you very much, and goodbye.